As Carolyn said, this is the first of 6, and we're going to talk today about an overview of the pavement design. And this is really kind of a high-level approach to this. We're not going to get into the nitty-gritty of pavement design, but in order to just kind of orient ourselves to what goes on in pavement design, how we got to where we are, and then a little bit about how we're going to move forward. It's interesting to note that this is a distribution. We've got about 3,400 miles of pavement within the state of Alaska. About 50% of our road is unpaved. Much of that is in the northern region. And when a pavement engineer talks about pavement, we not only talk about asphalt pavement, but we talk about gravel as well. So in my mind, and a pavement engineer's mind, a gravel road is a pavement. The surface of that unbound layer is considered a pavement, because a pavement's really defined as what you drive on. And so that's a little bit of a different view than a lot of people take of pavement. Most people think of pavement as asphalt or concrete or something like that. It's interesting to note between 2006 and I got this right out of the 2013 pavement report. Between 2006 and 2012, we've gone from about $75 million of welcome guys. $75 million of pavement restoration, rehabilitation, resurfacing, up to 104,000. That is good news in that we're getting more money. But if you'll look at the second slide, what you'll find is that the cost of the asphalt materials that we use in our pavement, if you will, is more than almost doubled. And so the reality is we're really putting down less material than we did back in 2006 if you look at it from that vantage point. So that's a little bit concerning for us, especially since we all know that our pavements in Alaska are not quite what we would like to see, the price of asphalt. Although it appears that in the last couple of years it has leveled off a little bit, and hopefully it'll stay there for a bit. And I don't know what this year brings with the price of crude oil going down, whether the cost of asphalt will go down or not. That remains to be seen, and we'll see what the bids come back in the near future. Maybe we're getting something out of all of this. The International Roughness Index, which is a means of measuring how rough our roads are. A new road it is on the order of 60 or so IRI. Alaska's really not doing all that well at an average in there, but we are seeing a slight improvement over time. But we have to be a little bit careful with this, because one of the things that's really biasing this a lot is our rough roads due to permafrost and frost heave. As a result of that, it's going to drag many of our pavements down, and it's going to be really difficult for us to overcome that, because that's really more of a maintenance function than a design function. It's due to the foundations of our materials rather than the design of the pavement itself. So when we look at these kinds of things, we need to be really, really careful about being mindful of what that is. It'd be really interesting to go take this and look at some of the roads like the parks and some of the other roads that don't have nearly as much problem with permafrost, and compare those to the Richardson and the Glen and some of those roads and see what that is. But the good news is we are tending to move upward a little bit. The present serviceability rating, which is a function of the ride, the cracking, and rutting, we are showing a little bit of good improvement. But even at this, a 3.0 is really considered fair. It's on a scale from 0 to 5. We are moving upwards, but we're really not doing as well as most states would consider acceptable. Again, some of this is due to our rough roads due to permafrost. Some of it is due to we just simply don't have the funds to repair everything or rehabilitate everything when we should. But the reality is it's not as good as we would like it to be. The goal for 2017 is a 3.7 coming out of our pavement management system is where we would like to be. Hopefully, as time goes along, we'll be able to achieve that. That's certainly better than where we are at today. Looking back in my memory, I look back at some of the roads information that we had way back in the early 1980s. We were around 3.3, something in that area. But we have a few more miles of pavement now than we had then. So we really are pretty much the same position that we were in the early to mid 1980s. Okay. when we talk about pavement design, it's really about knowing your materials. The calculations that go into it are really fairly straightforward. We've computerized that, but what we haven't computerized, and I don't think we'll ever computerize, is the materials. And so we have to understand our materials if we're going to be able to do a good job in our pavement design procedures. And we'll talk about that all the way through the rest of this presentation as to talking about our materials. The first thing we have to realize is every layer has to be able to withstand the loads that you put on it through all seasons, not just the summer or the winter or the spring, but all the way through the year. And it's really important to do that. And the response of each material is related to the response of the materials that are either above it or below it. They're all interrelated. So we can't just simply choose one layer to strengthen one layer if we don't pay attention to the rest of the layers and understand the properties of that. It's critical that we do that. We also have to know that unbound layers are going to deform because of load. We're just simply going to deform that. We'll go into that in a little bit more detail. And the bound layers not only deform under the load, but they also crack, either due to the load itself, fatigue cracking. Sometimes we call that alligator cracking, or chicken wire cracking is terms. I prefer the term fatigue cracking because it's truly representative of what's going on there. We have thermal cracking that's going on there as well, and deformation due to rutting, due to the material properties that don't resist that, and to abrasion, for example, under studded tires. All of those things go in that. And if you don't understand the materials, you can't do a very good job of designing your pavements. I don't care how good you are at running the mechanistic design software that we have. That's really easy to do, but the materials properties that you put into that are critical in order to make it work perfectly or make it work well for you. What I've seen on a number of occasions, people pull it out of the sky, or they pull out values that make the answer that they want to come out of it, and it doesn't necessarily represent what's going on in the field. If you truly understand these 4 points, you're an expert in pavement design. Okay? This is really all you have to know are these 4 points. And if you truly understand them, then you're going to be just fine. Unfortunately, very few people truly understand that. And that's where most of our failures occur. I've been involved in dozens of forensic engineering on pavements that have failed, and it failed for one of these reasons, one or more of these reasons, every single time. It's not because somebody didn't run the software right. It's not because somebody didn't put the right punch the buttons right. It's because they didn't put the right material properties in there that truly represented what's going on in that. Okay. So let's go through some of the basic concepts and definitions. There are a lot of them here. I'm not going to go in great detail in all of these, but as we move along. But I want to kind of give you some ideas of what some of these are and how they interrelate to each other. And some of them actually are in a little bit of conflict with our standard specifications because of the way we define things, and I'll point those out as we go along. Okay. The first thing is a pavement structure. A pavement structure is that portion of the embankment that sees the load of the tires that go across it. Okay? And those of you who understand some of the Boussinesq equations and soil mechanics realize that at some depth, the soil does not see the load on top of it for all practical purposes. Okay? And that depth depends on the properties of the materials and the weight of the load. Okay? So it's really critical that we understand that. And that curve there on the left-hand side is a form of the Boussinesq equation. You can see, as right at the top, 100% of the load on the surface, the pavement sees 100% of the tire loading that's put on it. And as you move downward, and once you get down to about 3.5 feet, for all practical purposes, it doesn't see that load anymore for highway pavement. Okay? And so if you look at that, if you understand that, and you make sure that each of those layers can handle the load that's being put on it, then life works out pretty well. If it can't, then we have problems. So for a pavement structure for most highway application, it's 3 to 3.5 feet. If it's an industrial highway, you may bump that up a little bit. but for all practical purposes. For airports, it's on the order of 5 feet. Now, I can't tell you exactly what that is because that depends on the materials that you're using. And the thickness of the asphalt, thickness of the base course, all of those kinds of things come into play as to figuring out exactly what that is. But nonetheless, we can calculate the stress or the strain at any point within that layer and making sure that the material can withstand that. Okay? A surface course. A surface course is what the tire sees. That is a very terrific. It can be asphalt, Portland cement, it can be surface treatment, it can be a gravel surface. Whatever the tire sees is considered our surface course. And it has a couple of different functions. The first function, of course, is to be able to withstand the tires. Okay? It's got to be able to stand the abrasion, it's got to be able to stand the loading, it's got to be able to withstand all those things that the tire brings to it. The second thing is got to be able to withstand the environment. Rain, cold, heat, all of those things which we normally think of as having to do with our environment. So we have to withstand that. And the other function of it is really to protect the base course. It protects the base course in multiple ways. One is, in some cases, it keeps the water out of it. Keeping the water out of it keeps it dry, keeps it within the right range of moisture content, which helps keep it strong. If it gets too wet, it loses strength. If it gets too dry, it loses strength. There's a range in which we would really like to keep it in. The other thing is it actually reduces the load on the surface, and we'll talk about that a little bit in more detail a little bit later, but it reduces the load so that the base course is strong enough to handle the load in which it's exposed to. So if we want to reduce the load on the base course, we have to do one of two things. Either thicken the pavement or the surface course, or we have to use a different surface course. A chip seal is not as strong as an asphalt, is not as strong as a Portland cement. So how we reduce that is by choosing the right surface course, and the right surface course, it has to be able to meet all of those criteria. Not just one or two of them, it has to be able to withstand all of that. And so that's what makes the materials science really critical in selecting the right course. We'll go into a little bit more detail in that in just a few moments. The base course, it's the surface, typically the layer right beneath the asphalt or the pavement surface course layer. It can be made up of a number of different things, but its primary function is to reduce the stress on the subbase to within allowable limits. That's its primary function. And we can do that again by changing the quality of the material that we use, stabilized or an unstabilized, bound or unbound material. We can do it by changing the thickness. But what we have to do is make sure that whatever load that the subbase is seeing is within the acceptable limits of the strength of that material. Okay? I think we're probably seeing a little bit of a trend here. The subbase is that layer between the bottom of the base course and the top of the subgrade. Okay? Its primary function is, again, to reduce the load on the subgrade such that it can withstand that based on the material it is. Now, this is where a pavement engineer and the Blue Book, our specifications, have part ways a little bit. In the Blue Book, subgrade is considered the natural ground. Okay? It's not the embankment. But to a pavement engineer, it is any material beneath the pavement structure, which for highways is about 3 to 3.5 feet. So it can be fill material for the purposes of getting grade, but it is not necessarily original ground as the Blue Book would define it. So be a little bit careful. I'm going to use subbase in here. I'm going to use subgrade in this as anything below the top, the bottom of the pavement structure. Okay, so that's a distinction. So keep that in mind as we go through that. But again, the sole purpose of the subbase is to reduce that stress on that subgrade level to the point that it can handle it, whatever the material that might be. If it's silt, then my pavement structure is going to have to be stronger than if it's good, solid, competent gravel. Okay, so there's a difference in there. Okay, subgrade, as we talked, is the top of the embankment or excavation upon which the pavement structure is constructed. Again, that's a little bit of a difference. And one of the things we want to do, the whole pavement structure, the function of that is to reduce the load due to the traffic on top of that, subgrade. Now, one of the things we need to do is make sure that we have a distinction between the load of the embankment and the load on the traffic. We do have to design our subgrade so that it can support the pavement structure, just the weight, the dead load of the pavement structure, as well as the traffic going across it. Our original ground, we have to make sure that we can carry that. That's all a geotechnical investigation. I'm not going to cover that as part of pavement design, but it is part and parcel to pavement design, because we have to assure ourselves that the subgrade can carry the weight of the embankment of the pavement structure, and that's critical that we do that. But that's not part of pavement design. We kind of cast that over to the geotechnical people and said, make sure that that stuff can handle whatever load we're putting on there for the pavement structure, and if it can't, what do we need to do to make it do so? That's a whole different technology or technique that we work on. So I'm not going to address that at all beyond mentioning that that's the case. So we put it all together. We've got a layer of our pavement structure sitting on top of our subgrade. And supposedly, if we do everything right, then we're going to get the design life that we choose, whether it be 15 years, 20 years, 50 years, whatever we choose to design for. Hopefully, it will all come together to make that happen. Some of that is due to our ability to construct it. Some of it, most of it, oddly enough, or I shouldn't say oddly enough, most of it, though, is really our ability to pick the right properties of the material for the application. If we do that, we see that that works out for us. When we don't do that, or we try to guess, or we try to convince ourselves that the contractor can work miracles and produce material that's not there, which I find happens far too often, we won't get the design life that we anticipated. Okay, so and choosing the right design life is critical, as we'll talk about in a few moments, but it's critical to what we're trying to do. We don't want a pavement design that will outlast our foundation, because that's just not going to work out really well for us. That's a waste of money. So we want to make sure we try to put that all together and putting it together. So when we're looking at a pavement design, and what we're doing is we're objectively looking at our pavement structure, and we have a system of layers such that each layer reduces the load on the layer beneath it so that it's within acceptable limits. That's really what pavement design is all about. So if you look at the example that we've got up here, you'll see two tires there, and the load is distributed. We usually see it going out in a conical fashion. The exact slope of that depends on the strength of the materials. It won't go exactly straight. It depends on the strength of materials that we have. If it's softer materials, then we'll kind of go out. It'll go out steeper. If it's not so good, it'll go out flatter. But nonetheless, we'll see that. So one of the first places we look is at the bottom of the pavement layer. We look at the horizontal strain. Okay, and that horizontal strain is a function of everything below that asphalt, and as well as the asphalt itself. So they're all interrelated. So we want to keep that within acceptable limits. And we have design equations that will say if you've got a strain of say 100 microstrains, it will last some length of time depending on the properties of the asphalt itself, or the properties of the Portland cement concrete, or the asphalt. When it comes to gravel, we don't worry about that. We really worry more about rutting and wear than we do horizontal strain. And then we look at the top of the subbase, and we look at the horizontal or vertical strain, and we make sure that that's within a set specified limits. We have equations for that will predict the rutting and then we repeat that for each layer beneath that. So the idea there is we are calculating at the top of each layer the stress, and then we're making sure that that stress is low enough that we get the life that we intend to get out of it. And that's critical. So we have to know the materials to put in our equations to make it work. And we can't shortcut that. We really have to understand that. And all the research that I've ever done in the last 40 years has proven that over and over and over again. It's really, we have to understand those materials. Okay? So let's step back a little bit in time and look at the history of pavement in Alaska. And in the early 1950s to the early 1970s, this was it. This was our design. And when I first came to work for DOT in 1969, this was our design. 1.5 inch pavement, over 6 inches of base, over 6 inches of sub-base, over 24 inches of bar, and we didn't really care after that. Okay? At least we understood at some depth it really didn't make much difference anymore as long as it could handle the weight. Bruce Campbell fought FHWA on this, and what we ended up with is something called interim pavement. FHWA required, back in those days, 3 inches of asphalt. Bruce Campbell says, well, no, we really need to get Alaska out of the mud, and so we're going to put down 1.5 inches, and we call it interim pavement. We're going to come back as soon as we get to where we need to be, and we're going to start overlaying everything. Oddly enough, for the traffic that Alaska had at that time, this worked really well. There are some pavements out there that exceeded 30 years under this design. Okay? So, Bruce Campbell had it right, in my opinion. We got what we needed. We got a lot of roads that got them paved. We got out of the mud, and it performed quite well for the traffic that we had in the 1960s and the 1970s. Then Alaska started to grow, and we had to do something a little bit differently. Okay? So then at that point in time, in the early 1970s, we decided that we're exceeding that. We really need to come back and do it a little more engineering here. And so we started looking at empirical design procedures. And empirical design procedures are really experience-based. And as such, it's limited to the materials, the climate, the traffic that you have the experience in. If you don't have any experience in, my empirical design here in Alaska will not translate to Texas. And California's will not translate to Alaska because it's not based on the experience of those that are using it. So it really requires that we be constantly reviewing and constantly updating an empirical design. And so if you look back in the history of, say, the AASHTO design procedures, you will see a constant evolution of changes in there as traffic changes, as material changes, all of those kinds of things. So this is what empirical design means. It's experience. It's empirical. So it's something weird. So our esteemed pavement engineer at the time decided that he was going to use the R value that came out of California. That's where he was from. That's what he had experience with. That was his empirical base. So he brought up something called the R value. There's the equation, really. The gravel equivalency over the subgrade is 0.0032 times traffic index, 100 minus the R value. R value is somewhat akin to a CBR. Not quite the same, but very good. So that was the whole equation right there. So all you had to do was plug that in there and you give a gravel equivalency. Each layer has a gravel equivalency. That's what the R value is. It takes that value and converts everything essentially to base course. And then you come up with thickness of those, and you start at the bottom, and you put enough gravel equivalency on top of that, in enough thickness of each layer, in order to protect the subgrade. It's called a subgrade protection model. It's protect the subgrade, and as you built it up, you were able to come up with a design. Odd thing happened. Designers would work their tails off to get 1.5 inches over 6 inches over 6 inches over 24 inches. Almost all the designs that came out of this procedure, that's what it was, right back to the old method. And they would adjust the values, the R values, in order to make that work for them. So as you can imagine, that didn't work out too well for us for a number of reasons, as we'll see. So Statewide Materials began a study in 1976, I believe it was 1977, when I joined research, to look at why some pavements perform better than others. There was 120 roadway sections that were picked out of that, and we measured everything we thought we could measure out of that. We measured deflection, we measured the gradation, plate value, asphalt content, all the properties of the asphalt, frost heave, just on and on and on. Somebody wants those notes. I still got the original notes that we took out in the field for that. I don't think you really want to try digging into that. But nonetheless, we looked at them, those 120 roadway sections, over a 3-year period, trying to understand why some pavements worked better than others. Some pavements lasted as little as 5 years. Some pavements lasted as much as 30 years. And so it was our job to try to understand that and come up with some conclusions. And what we found out was that a few things really came out of this. There's some other minor things I'm not going to bother to go into. But the major things that came out there, 2 inches of asphalt perform much better than 1.5 inches of asphalt. Okay? Those of you now, we now understand better why that was occurring. One of the things we knew at that time was if you looked at the specifications and looked at the tolerances, that 1.5 inches could be as little as 3/4 of an inch. 3/4 of an inch is 1 rock thick. Once you get down to 1 rock, you have no binding of the rocks, and they would just pop out. There was no fatigue, ability to carry loading and fatigue, and so they would just immediately, that crack around that rock would immediately be on the surface as a result of that. So that's one of the reasons. The other thing we've since learned since we went to the newer methods was, by the way, you should never have less than 2 rocks thick. Most people prefer 3 rocks thick as far as design goes, your thickness goes. So that is actually a limitation on the thickness of the asphalt you can have. A minimum of 2 rocks thick and preferably 3 rocks thick for whatever size rock you choose. But one thing we also found out later was that every inch of asphalt that you put on within the range Alaska normally uses will double the life of the pavement in fatigue. We found that. I don't know how many times I've run that analysis and keep coming out with the same answer. So if you want to double your life, just add an inch asphalt and you'll be right on. And from a life cycle cost standpoint, that may be a good thing for you to do. That's something that you as a designer have to figure out. We also found that the performance was a function of the deflection, maximum deflection in the spring. The higher the deflection, the lower the pavement life. And I'll show you a graphic of that in just a moment. So they were strongly related to each other. And so we also found out that the passing the 200 sieve was a really good indicator of the deflection. High 200 content, very high deflection in the springtime. Low, much better. But the other thing that did surprise us, for those who may remember the old frost heave test, and we still do that occasionally, we would put a sample in the freezer and allow the bottom to stay warm and the top to stay cold, and we would actually cause the soil to heave. The 200 was a much better indicator of the frost classification or the frost heave test, which was really a good thing because it's a lot cheaper to run that than the frost heave test. But the frost classification really didn't correlate very well with our pavement performance. And so that's why you don't see the frost classifications in any of our design procedures. We just walked away from that and we said we're going to focus on the fines content passing 200 sieve and let that go. Okay, here's a graphic of that. As you can see in the graphic on the left, as you increase the 200 sieve, you also got an increase in fatigue cracking, alligator cracking. But what's important also to note here is that the slope of that line indicates that as you get deeper, you can allow the fines content to increase. That goes back to what we said earlier, because the load at depth is less, and therefore we can allow that material to be weaker, and so we can allow more fines content without adversely affecting the pavement design life of our pavement, our surface. Really good thing. Again, we also did the same thing, applied the same thing with our deflection, and we found that as you increased it, it's interesting to note, 2% fines can make a huge difference in here. 2%. And yet, sometimes we don't pay enough attention to that, at least in this methodology. But again, we can see that as we get deeper into the soil, we can allow more fines without increasing the performance of our pavement, which is consistent with what we know from our equations for stresses and strains we move down. The stresses go down, we can allow the use of a weaker material, and consequently, we can allow more deflection at those layers. And so that's more fines as we move downward. And so that's something for us to remember. Okay? So in 1983, I just looked that up the other day. It's all 39 pages long. It's really short and sweet. Based on the a relationship between pavement deflection and pavement performance. This really was about. And the excess fines method basically says that at any level, if I exceed a percentage of the fines, then I need to take that into account. And then I have a point at which I will not allow any they're called critical fines. I won't allow any more than that. And so that was put in there. It was a numerical integration. We just added it all up as we went down. And then we also found that there's that relationship we built into that between deflection in that. And we assumed that the spring was the controlling season. Now that is true for a weak road, but it turns out it's not true for a strong road. It turns out the fall is that. So we did find out later that, but for the purposes of what we were doing at that time, that worked out really well. And we also found that the equivalent single axle loads that were on the pavement, which is 36,000 pounds on a dual axle vehicle, axles, we could not exceed 1 million. That was a limitation of what we did, because that was a limitation of our experience based on all the roads, 120 roadway sections. We did not have any that exceeded 1 million. So that was a limitation. We rapidly grew out of that in many cases. But for low volume roads, it's still a valid approach. And we do push it with the local governments because it's easy for them to do and easy for them to understand. And so we still see a fair amount of use of this, not at DOT, but at local roads we do see a fair amount of use of this. Okay, so in 1980s we started moving into mechanistic design because it allows us to use any material without changing our design methodology. As long as we can define how the material performs, we can use it. In mechanistic design, it's much more flexible in our layer selections than the excess fines method was. We can look at much more complex traffic loadings in there, and oftentimes I've done analysis to look at what would happen if we increased the legal loads on our pavements or did not put load restrictions on or something. You're able to do that very, very nicely. It does allow us to design for seasonal and climate variations. If we want to, we can look at this look on a daily basis, an hourly basis, but typically we usually break it down into 4 seasons. And there's no maximum traffic that we put on there. We can analyze all of that. So we've since moved into that. 1989, 88, shortly after the advent of the PC on our desk, we worked with Oregon State University, and we developed ACOD, which meant Alaska Overlay Design. We called it that because that was our focus as overlay design at that time, but it could be used for anything. It brought it to the desktop and automated the design process. You could push buttons and get out. That's still no better than the materials that you put in there. You still have to worry about that. We also looked at both new pavement and pavement overlay design, which excess fines didn't do a very good job as on the overlay design. And we could also use the same software for highways and airports. At that time, FAA allowed us to do that. They've since come up with their own, which is actually similar but not quite the same. Okay. In 1998, we reintroduced ACOD in a new version, which provided design in dual units, because for those who remember, we had to do it in metric for a while. So we put that in there. We also improved the user interface to make it a little bit easier for the designer to use. And then we updated the performance models in that because there's some new work that had come out by Whitsack and others that we put in there, and Asphalt Institute, that we put in there to make sure that we had the latest and greatest in there. And then, of course, we all are familiar with the 2003 Alaska Flexible Pavement Design, aka PFD, and that's the one that we're currently using. It did a number of things for you. One is we improved the user interface on that dramatically. We allowed the use of both the mechanistic and the excess fines method in there, which helped. The flexibility in that is amazing, and what you can do if you know how to read all of the outputs out of that. You can actually look at the stress and strains anywhere that you want if you want that level of detail, or it will just simply tell you whether it passes or fails, and it will tell you which layer failed in there, and so that you know where to put you at. It provides a database of some of the materials properties in there. One of the things that probably needs to be done, Mike, is to upgrade that, because that's we have a lot more information now than we had when we did that. I think Steve Sabunja and Bob McCaddy and I sat down and summarized everything that we knew at that point in time. That's probably time to be updated in that. It also, again, updated the performance models to the latest models at that time in 2003, which seemed to be pretty good for now. Some point in time, we may want to take another look at that. It gave us a lot of detailed information, and for the first time, we actually wrote a manual on it so that everybody has access to that documentation. For those of you that are here, we are in the process of updating that so that it will run on Windows 7 and Windows 8. That should be available hopefully by June 30th. We are diligently working on trying to make all of that happen. Okay. Some of the things we need to consider in our pavement design, we need to understand our anticipated and expected performance. What do we expect out of that pavement? We need to define that in our own minds. Are we going to limit the rutting to 1/2 inch or 1/4 inch? Are we going to have 20% cracking in 10 years or 0% cracking in 10 years and something else in 20 years? What are we expecting out of that? We need to understand the first cost and life cycle cost, because the life cycle cost may lead you one direction and the first cost will lead you to another direction. And first cost, we're going to try to keep the minimum cost, but it might not work out very well for us, and we may be rehabilitating that in 5 to 6 years, when just for a little bit more money we could get 20 years out of that payment. Impact on maintenance. That has a significant impact, as Joe Perkin, Commissioner, proved to us in no uncertain terms. He basically said, let's go out there, pave it, and we'll find the bad spots and we'll deal with those as we move along. Not a bad philosophy, but that's something that I don't think that's the way to do it all the time. What's the impact on the public? If we're out there having to especially in urban areas, which we'll have a whole session dedicated to urban areas, having to come in and rehabilitate that pavement in urban areas. Available materials. This is where we have a lot of problems. It's probably one of the biggest problems we have, is not being realistic in the materials that we can produce. So I've seen designers go out there and put values in for those materials in the hopes that the contractor, as I said, can work miracles. They want 6% fines when reality the material in the source is 10%. How are you going to get rid of that? 4%. And it's caused a lot of problems. So I just suggest that we be realistic when we select our materials as to the properties that they're doing. And then is that pavement structure constructible? We had situations where it wasn't, and we need to make sure that it is. There's a lot of different surface courses we can choose. We need to talk about our foundation, traffic, available materials, climates, and design goals. All of those things come into play when we look at that. We certainly don't want to put down a high-type pavement over a foundation that's going to have to be repaired every year because of settlement or thawing. We want to balance all of that. If we got high traffic, low traffic, we're going to do something different in those instances. Make sure we have what materials do we have? Are we going to have to haul them in, or are we going to have to modify them in some way? We need to worry about that. Our climate, it's changing realistically. We need to be thinking about that. And then again, our design goals. How do we want it to perform as time goes along? We always keep that in our head. We want to select our material according to the foundation. In this case, we're on this is a section of roadway just west of or east of Fairbanks. That's after 2 years of no maintenance. It was an abandoned section of road. It's 2 years after maintenance. So that you can imagine what maintenance was doing all these years trying to keep that level. I love doing this to the legislature. They want to cut maintenance. Okay, our roads can look like this. That's fine. But we want to make sure that our surface life, the material we pick in our pavement design, is consistent with this. We want to, if it's going to be like this, we want to make sure that we give maintenance something that they can work with as part of that effort. This is one that I've struggled with over the years. Don't let the 10% guide the 90%. I've seen situations where we will design a pavement for the 10% of the road that's got a problem. And as a result of that, we spend a lot more money than we probably should. One of the things we want to do is delineate that 10%, deal with that on its own, and then deal with the rest of the 9% on its own. In some cases, we may just let it go downhill and let maintenance take care of it. We may come up with another solution, but don't design for that 10% because it will often cost you a lot more money than you should be spending. So one of the ways to do this is break your project up into segments that are uniform and designed for each one of those on their own merits, and try to work with that. Of course, you do have to pay attention to the constructability issue. You don't want, as we did one time, we were breaking it up in 100-foot chunks, and that cost us a tremendous amount of money because the contractor was changing, going in and doing a 100-foot chunk. Well, he couldn't even get his equipment lined out before it was on. So we found out typically something on the other 1,500 feet is probably a more appropriate means of breaking that down in order for the contractor to do that. Exactly what that length is depends on how radical the changes are in there and the transitions are in there, but it's something to be thought about. We also want to protect, make sure we select our surface course that can withstand the fatigue. That may mean that we modify it, or we choose a different grade of asphalt in some cases. We want to make sure that it withstands rutting. Rutting comes in a number of different forms. One is permanent deformation. That has to do with the properties of the asphalt mix. Whether you've got the right gradation, the right asphalt content, the right asphalt cement. All of those come into play. The other part of rutting is due to abrasion due to studded tires. We'll talk about it in a minute. We're implementing a hard aggregate policy to try to get past that one. Abrasion can come not only from studs, but it's just simply the tire wear that's going across it. It's shoving. That's a property of the asphalt itself. That's when the asphalt, as people are moving out, it gets pushed off to the side. It's akin to rutting, but not quite the same. You can see some extreme examples in intersections where it wasn't designed, where people are stopping and they're pushing the asphalt, and you'll see a sort of a rut, and then you see a hump right where people are stopping. That's a form of shoveling. And then raveling. Raveling usually occurs because you don't have enough asphalt in it, and so this whole thing is a balancing act with the materials that we're talking about in order to get what we want out of it. And that's where your materials, mixed designs, and all those materials people become critical to you in order to make that happen. And don't just assume that this is all going to occur on its own. It has to be planned, it has to be in the specification, it has to be in our procedures in order to make that work. Okay? One of the things, again, we want to talk about available materials. Make sure the materials are available to construct whatever surface you're going to make out of it. Again, I've seen a number of instances where a designer just assumes that it's going to be there, and it's really not there. A little bit of upfront work going out there and making sure the material's there. And if it's not there, what are you going to have to do to make it work, or are you going to have to haul material in, import material in to make that work? Those are all decisions need to be made up front, not after the fact, and when it's going to cost a lot more to resolve the problem. A climate, within the climate that you've got, can it be put in within the specification? If you're anticipating it being put in late in the year, you can run into problems if you don't have the right material, or maybe you shouldn't do it at all. Sometimes you're forced into it. I've been forced into it because the director says that will not sit. It's gravel over the winter. So do I put temporary pavement in, or do I put in something that hopefully will work? Stabilized base, oddly enough, works really well in that situation. It gives you something down that you don't have to take up. But I've done it at zero, and it's still there. It doesn't mean you can't do it. It's just you got to put a lot of effort. And does the climate affect to favor one surface over the other? Up on the slope, we're tending to use Arctic grade asphalts more than we do here in the interior. In Anchorage, they're tending to use modified asphalt as much for traffic as anything else. But you want to make sure that you pick the right material for the climate that you're in. And Alaska has a really large climate base. What works in one area will not necessarily work in the other. So we need to be paying attention to that. Design goals, we've kind of gone over some of these kind of things. But expected life, performance, rehabilitation strategy. What do you plan to do when it wears out? Are you going to overlay it? Are you going to mill and fill? Are you going to do full depth reclamation? You need to be thinking about those things as you design the pavement for today. How are you going to rehabilitate or reconstruct that thing? What are you going to do in the future? because what you do today is going to impact those decisions as you move down the road. So think about them today. What are our system goals? One of our system goals is by 2017 to improve the PSR to 3.7. Okay? So how's what you're doing going to affect that? Want to be paying attention to that. Financial goals. You know, Bruce Campbell wanted to get us out of the mud. That was his financial goal, the money he had. Not a bad one. We have different financial goals today. We need to be thinking about that. All of those things go into your design criteria as much as anything else, and you need to be paying a lot of attention to that. Talk just a little bit about a couple of the services. Surface treatments. Surface treatments are good for low volume roads. There's nothing wrong with a good surface treatment. It's also good for poor foundations. When I say surface treatment, I'm talking about not only chip seals, but high flows. They work really well in poor foundations. Maintenance loves them because they can come in, grind it up, lay it back down, level and seal it back over, and they can do that like miles a day. It's really, really fairly inexpensive for them. But where they've got good foundations, they want asphalt because it lasts longer. Okay, it requires a good pavement structure. Don't think because you're going to use a chip seal that you can get away. Actually, it takes a better pavement structure than asphalt concrete, because it has no strength. So if you don't put in a good pavement structure in there, it's going to break up very, very quickly, and you're going to wonder why. You really want to make sure. If anything, you probably need a better pavement structure on surface treatments than you do hot mix. It does not do very well in turning situations, so if you've got an area where there's a lot of turning movements in there, you may want to choose to do something else. The typical life is 5 to 7 years, although I have seen some surface treatments out there that are 25 years old. Hurst Road is a good example of that. Before it was repaved, Black Road in the Fairbanks area, they have done very well under some circumstances, but in most cases, this is what you can expect out of it. There is an asphalt surface treatment guide that's out there, written by Bob McCaddy. It is on your website. I encourage you to, if you're going to be using surface treatments, to download that. It's got just pretty much everything that you ever wanted to know about those surfaces. Hot mix. It provides increased structural capacity. In other words, it adds strength to the pavement, unlike a chip seal. It's got good wear characteristics if it's designed properly and the mix is put together properly. It's got a smoother surface and a quieter surface than surface treatment. That's one of the complaints people have about surface treatments, is they tend to be a little bit noisy. There are some things you can do to reduce that, but in general, that's the case. They typically have a long life. We typically like to get, I think our average is between 12 and 15 years right now, although we have seen some that are in excess of 30 years old, but we're getting a lot better performance out of those overall. But they are more expensive. And in general, they tend to be pretty low maintenance. There's a little bit of crack sealing that we need to do in there, but that's pretty much all we have to do to maintain those. Okay? Something that is in your design book, and I suspect most people don't even realize it's there, we call it the Alaska Renewable Pavement. In some parts of the world, they call it perpetual pavement. We didn't quite get all the way to perpetual pavement, but close to it. It doesn't take much more to get all the way there. It's basically what we're doing is we're thickening the pavement structure such that we guarantee ourselves we're going to get 35 years out of it, which is almost perpetual. The idea there is that we've got indefinite fatigue resistance in there, and we're going to simply resurface the top 1.5 to 2 inches on a periodic basis, and the rest will stay there for pretty much indefinitely. And so the reason we like these, especially in urban areas, is because they have far less impact on the traffic. It is possible for us under Alaska Renewable Pavement to come in and replace a pavement literally overnight. We can mill it and pave it in one night if we schedule everything out. In many cases, what we do is we'll come in and we'll mill it, and then a day or so later we'll come in. The public is always on pavement. So it has minimal impact on businesses, has minimal impact on high traffic areas. So in those situations where you have a lot of traffic and potentially high impact on the public, Alaska Renewable Pavement, or perpetual pavement, as some people call it, is a really good way for you to be thinking and adding in there. It is defined in the in your pavement design manual in some detail. We now have a stabilized base policy. This came out of frustration of our then chief engineer, who was finding that a lot of folks were hoping that we keep the fines content down. So he said, okay, we'll solve that problem. We'll just stabilize it. Stabilize it means a number of different things, a number of different options here. The full depth reclamation and all its forms in there. Basically what the book says, if we can get a modulus of 85 KSI or better, it's considered stabilized, and it's working pretty well. It took a little bit of getting used to it at first, but most people don't even question it now, and the cost of it is pretty minor compared to what it was when we first started. So I don't think that I think that's working out. There are some exceptions to that. If you've got a gravel to pavement project, which we don't have too much anymore, but when it was put in, a low average daily traffic for some of our low volume roads is not required. If you have an unstable foundation, it's not required, but oddly enough, one of the things we're finding is that on unstable foundations, a stabilized base will actually help lengthen the time that pavement is going to last before it has to be rehabilitated. We did that on a number of roads on the Elliott, a number of projects on the Elliott, and it surprised all of us. We were getting a much longer life before we had to rehabilitate it, and before it settled out and had to be leveled and patched. We had one of the requirements is that you have to do a life cycle costing analysis. That proved it's not cost effective. I don't think anybody even bothers with that anymore because they just do it. And if we're designing a project for another agency and they don't want it, then we don't have to put it in there. So these were, believe it or not, this took longer than the rest of the manual did. It took us 2.5 years to write the 3 pages that has a stabilized base policy in there. Okay, there is a new stabilization manual that just came out in December that's available for you. We added some information about different types of stabilizers, including geofibers and cement and liquid, some of the new liquid stabilizers. Those are all in there for you to use, so that was updated just recently. One of the more popular things that we're doing these days is foamed asphalt. Foamed asphalt is really an interesting technology developed in the South way back in the 1950s, and then we had to buy it back from the South Africans a few years ago because they developed it a lot further. But basically, if you take hot asphalt and mix it with water, it will foam up to about 10 times the size, and it makes it very easy to do in full depth reclamation. In the Parks Highway just outside of town, we were able to reduce the cost of rehabilitating that pavement by 50% by using that. Otherwise, we would have had to haul in low fines content material from the valley here up to there, and by using foamed asphalt, we were able to save a lot of money, and it's performing quite well. There have been a number of instances around the state where we've used that, and we continue using it, and it's working out really well for you. It's just one of the many available to us. There's a new hard aggregate policy that's coming in there, and Steve and I and Mike Santangelo, Steve Sabullion and I and Mike Santangelo are going to be working on this into the new pavement design manual that will become the updated pavement design manual, will be coming out here by June. And hard aggregate used on all roadways of 5,000 or greater. There's something called Nordic abrasion, which is readily available. There's a picture of it there in the lower right corner. 8% or less. If you go to Scandinavia, 7% or less. So Scandinavians are it was originally based on a lot of work that Bruce Burnett did in Southeast. My understanding that that pavement is more than twice the life of the original pavement and still going strong on Egan Drive. So we know we can get, at least on Egan Drive, we got at least twice. Looks like we're starting to shoot towards 3 times the life out there. So we know it works. I commissioned a study back in the early 2000s by Quality Engineering to look at that, to look at the cost effectiveness of it, and it turns out that we can afford to haul the coarse aggregate all the way from Seattle and still be better off from a financial vantage point than we would be just continuing to do what we're doing. So it is done. And again, it's going to be put in the new pavement manual that's coming out soon. So in summary, knowledge of materials is critical. You cannot bypass that. Everything that we're doing in pavement design is based on understanding the materials. The rest of it is easy. The materials part is what really goes. We also need to know how the materials properties vary with the seasons. Some actually get stronger in the spring, some get weaker. Some get weaker in the fall, some get stronger. So we really need to understand that. We're always going to keep the stresses and strains in each layer to within acceptable limits. We can't violate that if we're going to expect good performance out of that. And the surface course must be able to stand all of the loads, the abrasion, the environment, all of the things that go along with that. So it's again, we need to really understand our performance in that respect. So with that, I'll be happy to entertain any questions that you might have.
Billy, the IRI roughness is trending up or worse, is that correct?
Trending up is worse, yeah.
And do we have resilient modulus data on our material sources? Do we have modulus data on our main pits where we're getting?
We have some.
Okay.
And Newt Bingham has been doing a good job of going around and measuring those with a falling weight deflectometer and back calculating those properties.
Okay, so they're all back calculated. Have we run any, like when we take quality samples from our pits, do we run any?
We don't run them in the lab
at all?
No, we don't run them in the lab. The only data that we have is by calculation.
Have you seen the automated plate loading test that Dr. White has developed from Iowa State, where you can do those in the field accurately with multiple cycles?
Yeah, I've seen that one, and there are several other methods to do that as well.
Is that more accurate than the falling weight?
We don't have the basis to say it's more accurate or not to compare it. That would take it may be better for where he is, or it may be comparable where he is, but if we go to some other site around the country, around the world, we don't know.
He's interested in coming up here to do some projects with us this summer. Is there a project you'd be interested in doing some comparison between falling weight?
Yeah, we'd be happy to do that, but I would talk to Carolyn as to how we go about that, or Mike, and we'd be happy to participate in that.
The last question I had was, what is Miner's Law?
Miner's Law, sorry. Miner's Law says that every time you load it, it's using some percentage of the load. So the
incremental failure.
Incremental failure, some percentage of the load.
A portion of the easels
right.
that you designed.
So when you add all those up, they equal 100% or less. Okay. If once it exceeds 100%, it's failed. Okay.
I have one question. Billy, you mentioned weak roads versus strong roads with regards to seasonal weakening and controlling. Mm-hmm. So how do you define weak roads versus strong roads?
One way to define it is structural number. Okay. That's one way to do it. And if you look at the AASHTO equations for the fatigue life, or the calculation for easels, it's the weight of the load that you're putting on it over the standard load to some power.
Right.
That power is a function of the structural number. And so as that power goes, as the road gets weaker, that power goes up. As the road gets stronger, that power goes down. And so in the springtime, if we got a lot of thaw weakening, then that power is going to go up. Okay? And so the critical time becomes in the spring. Right. If that power does not change significantly, for Alaska, it tends to be in the fall because that's when we tend to get the most rain. But okay.
If you find weakening, then it's in the spring. If you don't find it, then you should look in the fall.
Right. And the nice thing about it is the design software that we've got points it out in spades. Any questions from the audience or those online?
None here in Anchorage.
Not in Anchorage? How about Juneau?
Nope, not here. We look okay. We're experts now.
Any additional questions here or comments? Okay? Well,